Thank you for coming to this talk. This is joint work with Subhash Koth, and I'm going to be talking about almost polynomial factor inapproximability for parameterized k-Clique problem. So there are many optimization problems that we care about. It turns out that most of them are NP hard, and there are ways to cope with this NP hardness, and one of them is approximation algorithms. So suppose the exact solution, finding it is NP hard, maybe in polynomial time or efficiently we can find approximate solutions. And it turns out that for many interesting problems, even this is NP hard to get some good approximation algorithm. And in such cases, we go towards finding fixed parameter tractability solutions. For instance, for the vertex cover problem, finding a 2 approximation is easy, but doing better is conjectured at least to be NP hard. But if you look at the fixed parameter tractability of it, vertex cover is fixed parameter tractable, that you can find some f of k times poly n, where k is the size of the vertex cover and n is the input graph size. We can find some vertex cover of size k in this time for some computable function f. But for many interesting problems, there is no fixed parameter tractability or a good approximation algorithm like set cover, clique, set intersection. So they are hard to cope on both fronts. And this gives rise to this new direction, which is to find fixed parameter approximation algorithms. So the main questions that we kind of look at in this area is like, is there an f of k times poly n time algorithm that approximates to a factor t of k, where n is the input size and k is the parameter of interest, which is the size of the witness, and f and t are some computable functions. So let's precisely look at the case for the clique problem. So here we are given as input a graph G, and we would like to determine if there is a clique of size k or not, where k is part of the input. And in the FPT setting, it would be considered a parameter, a fixed parameter. Now, of course, if I just output any vertex in the graph, it would be a k approximation to the solution, to the optimal solution. And in the NP world, we can say that you can't really do much better because outputting a vertex would also be an n approximation. And to do anything better, like n to the 1 minus epsilon better, like is NP hard. In fact, there's a stronger result than this, but let's stick with this. And in the FPT setting, this is the canonical W1 complete problem. So it is believed not to be having a FPT algorithm. And it was a long-standing open problem whether we can find any approximation algorithm or prove any hardness of approximation result in the FPT setting for the k-Clique problem. And recently in Stock 21, Binkai Lin showed the first result. It was a very huge result that to find any constant factor approximation algorithm in FPT time is still W1 hard for the k-Clique problem. And in this paper, we improve this gap to rule out any k to the little of 1 factor FPT algorithms for the k-Clique problem. Okay, we show that that is W1 complete still. So that's the main result of the paper. And in order to tell more about our result, I want to actually start off by telling like the big open problem in this area, which is the following. It can be dubbed as the PCP theorem or PCP conjecture for FPT or parameterized complexity. So let me start off with what a 2CSP is. So you're given as input a graph, an alphabet set sigma, and a set of constraints. So for every edge in the graph, we have a set of acceptable pairs in sigma cross sigma, which satisfy that edge. And the output is to find an assignment which gives a label in sigma to every vertex such that you satisfy as many edges as possible. Okay. And now, of course, in the NP world, this is the classic PCP theorem. And the PCP theorem states that to distinguish the case when there is a satisfying assignment which satisfies all the constraints versus satisfying, say, at most 0.99 fraction of the constraints is still NP hard. And then we can ask in the FPT setting, if we parameterized by the number of vertices or the number of variables in the 2CSP, what happens? And it turns out that exactly solving it is W1 complete because there's a straightforward reduction from clique. And then the question is it W1 hard to approximate when you parameterize it by the number of variables? So this can be dubbed as the PCP theorem for parameterized complexity. And it is already known that if we had this version, it would imply many things already in parameterized inapproximability. And this was very succinctly formulated as PIH, parameterized inapproximability hypothesis, which asserts that there exists some delta, some constant delta, such that it is W1 hard to approximate a 2CSP on k vertices. So k is our parameter, and alphabet size n. So clearly we can go over all possible assignments, which takes n to the k time. But is there some, say, 2 to the k times poly n, independent of k, time algorithm that can distinguish the case when the CSP on k vertices and alphabet size n has a satisfying assignment versus every assignment failing at least delta fraction of the edges? And this is conjectured to be W1 hard. So this is still the big open problem, but let me try to put this in framework of how things are known and what is the technical contribution of our work and the previous work of Binkhailen. Okay, so just to state again the results, Binkhailen showed that approximating k-Clique to any constant factor is W1 hard, and we improve this to rule out any k to the little of one factor. Okay. So let's see that if we had this PIH, then I want to say that one can rule out constant factor hardness for clique. Okay, how do we show this? It is known, what is known through as the FGLSS reduction, which is possibly the first NP hardness result that hardness or approximation result that was known. And this combined with some sophisticated PCPs and graph products is what yields the best results that we know for the clique problem in the NP world. And the proof I want to show now is that assuming the parameterized inapproximability hypothesis, which we just saw in the previous slide, we can show that approximating k-Clique to any constant factor is still W1 hard. So I want to show this proof because this proof sort of sets the outline for our technical contribution and Binkhailen's insights. So let's see the proof. So we are given a starting point would be a 2CSP, which is a graph on graph G on alphabet set sigma and constraints pi e for every edge E. And we will construct a graph of the k-Clique instance where the vertices of the graph are every edge in the original graph G and every pair of assignments to the two vertices in that edge will form a node in H. Okay, good. And the k parameter is just the number of edges of the original graph G. And what are the edges in H? So we have an edge between two nodes in H if one of the two things hold. Suppose the two edges E and E prime. So let's label the two vertices in H as E comma sigma E and E prime comma sigma prime E prime. And now if E and E prime in G did not even have a common vertex, then we just put an edge between those two guys in H. But if they had a common vertex, then both E and E prime have an assignment to that common vertex. And if they are consistent, then we put an edge in H. Okay. Now, in the completeness case, if there was a satisfying assignment to the 2CSP, then we can just look at the every edge and the pair of values that is given to the two vertices according to the satisfying assignment, and that gives you a node in H. And you just pick all of those nodes and they're all consistent with one another. So you have a clique of size E, which is the number of edges in the original 2CSP. And of course, in the no case, if you had a large clique in H, then what you can do is that because these large clique is just you have a bunch of edges, and notice that they're all consistent. So you will never have two edges of G. You'll not have two vertices in the clique which correspond to the same edge in G, because they will not be consistent. So you basically can stitch together an assignment, a global assignment to 2CSP, which satisfies a large set of the constraints. And thus you will recover an almost satisfying assignment to 2CSP, which in the soundness case does not exist, which is a contradiction. So there is no large clique in H. So this is the outline of the FGLSS reduction. And Lin's observation was somewhat very insightful, that we don't need this full power of the parameterized inapproximability hypothesis to get a constant factor in approximability of clique. So just to go back, here what we can show is that there is no 1 minus epsilon times E sized clique. And then using a standard graph product, you can rule out any constant factor approximation for clique. Okay. And so Lin's observation is that you don't need this power. In particular, if one has more information about the 2CSP, that the host graph of the 2CSP is the Boolean hypercube, and only the constraints, the predicates, can be changed, then we can actually get something stronger. So for that, let me just define what the Boolean hypercube is. It's the vertex set is all t-bit strings, and we have an edge between two vertices if they differ on exactly one coordinate. So they just change in 1 bit, or their Hamming distance is 1. Now, we can formulate something called the weak parameterized inapproximability hypothesis, which is that there exists some constant delta, such that given an instance of 2CSP where the graph is not G part of the input, but is QT, so that's fixed, but the input still describes what the constraints are, and the alphabet size is n, then it's still W1 hard to distinguish the case when phi has a satisfying assignment. So we have a weaker soundness here. Notice that the edge set of Qt can be partitioned into T parts based on which coordinate the edge is changing in. And we only want that for every assignment, on one of these parts of the edge set has a constant fraction of the edges being violated. So this is a much weaker result. If you look at it globally, we are not saying that a delta fraction, a constant fraction of the total edges failed, but it's in fact 1 minus 1 over t fraction roughly. But what we have is that if the graph is more structured, it's the Boolean hypercube, then we can allow for this weaker soundness, that give me an assignment in the soundness case, and I will find you a part of the edge set, one of the I in T, such that only in those edges a constant fraction of the edges are violated. Okay. Now we don't know how to prove this version as well, but we can come to a very strong conclusion with the same FGLSS analysis that even with this weaker version, we can get that we can rule out a constant factor approximation for k-Clique. Okay. Now, but this is a very insightful observation because we'll be using this later. Note that we don't know how to prove weak PIH as well, but this will be used. Even a weaker version of this will be proven, and that will be used eventually. Okay. So how does Lin's proof look? Lin starts from the k vector sum problem, which will be defined in the next couple of slides. It's essentially you're given k collections of vectors. you want to find one vector in each collection such that they sum to the all zeros vector over some finite field. And once you start from there, using the standard PCP tools, Lin proves some weak version of weak PIH. So it's a much weaker statement. But then develops a very novel modification to the FGLSS reduction. And that gives the some 1.99 approximating clique is W1 hard. And then using graph product rules out any constant factor. Okay, so that's Lin's framework. And our result is a modification at several levels. And the first one is that his k vector sum is over F2, whereas we will start doing vector sums over FQ. And this will require linearity testing over FQ in the low soundness regime and various other technical tools. And then we use the list decoding of Hadamard codes over FQ. We prove certain theorems and we use that. And because we do list decoding, this induces a lot of noise. So we need to do some very careful arguments in order to handle all this noise. And of course, unlike Lin has this modular framework of going from vector sum to 2CSP and 2CSP to clique. For us, the analysis doesn't cleanly go through like this. So we have a direct reduction from vector sum to clique. And the analysis sort of just has to handle directly analyzing at the clique level and telling something about the vector sum problem. Okay. So again, I will not go into what we show, but only first highlight what Lin's framework is. And then again, repeat what I just said now, but with more details. Okay, so let's look at what the k vector sum problem is. Here you're given k collections of vector of h log n dimensions over F2. And we need to determine if there is one vector in each collection such that the sum is the all zeros vector. And we start from this and we use the PCP tools in order to do some zero testing, basically. And we know this k vector sum problem is W1 hard. It's W1 hard over F2 and over FQ in general, even when H is like k square. Okay, H is the dimension. It appears H log n. Good. Now, what does this outline have? It has two tools. I won't go into the detail of what these tools are, but let me just say that there is an encoding function G, and it's good to think of it as some error correcting code, which takes h log n bits field elements and outputs 2h log n field elements. So there is some encoding that's done. And then after that, there is some hashing that's done, which takes these vectors in 2h log n dimension and then takes a vector in h dimension and then sort of partitions the 2h log n into chunks of size h. So you have 2 log n chunks, each of size h, and then takes this one vector in h dimension and these one chunk and takes the inner product in some sense. So you get a vector in 2 log n dimensions. So there is this hashing that's done. So you eventually start from h log n dimensions and end up in 2 log n dimensions. And note that h is like k square. So eventually you're going down in dimensions. So it's some kind of a hash function that happens. So I won't go into the details of what these things are, but let's look at two properties that we will need. One is that every linear combination of vectors in U, so U is these k collections of vector. So if you take any k linear combinations, any k vectors in U, and you sort of look at them under G, none of them will go to 0 if they individually didn't sum to 0. So if the k vectors themselves didn't go to the all zeros vector, then under G they will still go to non-zero vector. And the fact that you look at some 2 alpha and beta which are distinct, which are like the seeds of the hashing, and you look at U, V, and W, and somehow these things, even under hashing, when you look at the encoding of W plus U and W plus V, even when you hash them under different seeds, they won't go to the same thing. So there is this collision don't happen, and you need these two properties. I wish I could explain this in more detail, but I'm running out of time. So let's assume there are these collision properties, that non-collision properties that we have from the hashing. And then the construction of 3CSP is just standard. It's just you look at all possible. So the witness is going to be k vectors, one u1, u2, uk. And what we are trying to do is trying to sort of come up with the seeds of the hashing as the variables of the 3CSP. And the assignment is going to be is the hashed value of the seeds onto the of the witness is going to be the assignment that we are looking at. So if we had u1, u2, uk, and you had the variables, so a variable is going to be a k tuple over fh, which is alpha 1, alpha 2 up to alpha k, then we just look at the hash of u1 with alpha 1, u2 with alpha 2, and so on, and then sum them up. And that is going to be the assignment that we would want for that particular variable, which is going to be in the alphabet set f2 log n. So that's what I've said here. So if you take the k seeds and your u1, u2 were the actual witness, then you would want the hashed value sum. And of course, if u1, u2, uk sum to 0, then this would just be 0. And what we'll do, the constraints will be a linearity testing and membership testing. So, and zero testing, which is like the standard PCP framework. So linearity testing will ensure that your things are some related to some kind of Hadamard code words. And then the membership testing is just that making sure that the values you give actually correspond to the hashed value of some vector in your UIs. And then there's a zero testing to make sure that they sum to 0. So again, I won't go into the details here. And then the construction of the graph, you'll have to come up with some modification. So the idea is that the linearity testing is a predicate of arity 3. So we'll just go over all possible triples whose sum to 0. And then the remaining 2 testing gives you predicates of arity 2. So we can actually encode the constraint itself as an edge in our k-Clique graph. So this is the insight that is there. So our vertices are going to be all tuples in F2HK, F2HK, such that the assignments to these sort of are consistent with the linearity test. And the edges sort of capture the vertices capture the linearity testing, and the edges capture the membership and zero testing. And so that's how the graph is built. And of course, for us, we can't do things over F2, so we'll have to do over FQ. So the geometry changes, because now over FQ, the edges become like lines, and you'll have to handle a lot of noise and everything. So it's very technical, these things. So I'm going to skip talking about them. So all I wanted to say is that, okay, approximating it to k to the little of 1 factor is W1 hard. Although the ideal result we would want is approximating to any f of k factor, like k to the 1 minus little of 1 should be W1 hard as well, which we can get under gap ETH, but we are still far away from these techniques. And as such, the big prize is here, the parameterized inapproximability hypothesis, and I wanted to highlight that again. Now, one more, high-level remark is that we have a bunch of techniques for gap creation in parameterized inapproximability, and they're all very distinct. Like, one uses just error-correcting codes, the others uses extremal graph theory, extremal combinatorial objects. Now we are using locally decodable codes and list decodable codes. Somehow there is no common framework like it is in the PCP, in the NP literature, where you have long codes and things like that. So these are all seems like coping mechanisms, and it's stark contrast with the NP world. And maybe proving the parameterized inapproximability hypothesis might lead to a unified framework. And also, I need to say that one can get PIH, assuming the exponential time hypothesis. This is a recent work that shows this. But it requires some strong result that k-Clique requires n to the omega k log k time for even constant approximation. But we are very far from proving such a time lower bound for constant inapproximability of Clique, because both our work and the work of Lin can only rule out n to the log k to the omega 1 time algorithms for constant approximation of Clique. And there was a recent work which improves the exponent of the exponent to 1. But still, we are very far from getting the n to the omega k over log k time lower bound for constant approximation of clique, although it should be morally the correct answer. So that is one approach towards PIH from ETH, which is a stronger assumption than W1 hardness. Thank you.